Hi, my name is Gerhard Klimek. I work at Purdue University, and I'd like to talk with you about the nanoHUB platform, where we have over 2 million annual visitors and users. And it's a cyber infrastructure where we share nanotechnology knowledge, simulation tools, and lectures. We have over 3,600 contributors in 122 countries, where we have users that are typically faculty, students, and industry practitioners. It's instructive to also see this interactive picture more in a static form, where you can see that in an annual view, we have people all over the world interested in nanotechnology, wherever there's a civilization that can have the energy to light up the night sky. So let me tell you a little bit more about nanoHUB and its inspiration and what it does and what it tries to achieve. So the inspiration really stems from a significant investment into nano research, where the United States invests about $2 billion in nano research, and lots of software and data are generated. However, the broader audience cannot learn from these artifacts because they're typically not accessible. And therefore, we created nanoHUB that converts these resources into usable apps that are now having a global user base. With that, we developed a vision to really accelerate innovation through user-centric science and engineering. And our mission is to make the science and engineering products that are available, usable, discoverable, reproducible, and easy to create for a bunch of people, for learners, educators, researchers, and business professionals. So these are a bunch of lofty words, but let me fill in some numbers here. So what do we have? We have 600 nano apps that are running in the cloud. We have over 5,000 lectures and tutorials in over 110 courses. We have been a MOOC for many years. It's a cyber infrastructure that's running 24/7 with 99.4% uptime over the year. We have research impact. The nanoHUB tools and simulation engines are now listed in Web of Science and Google Scholar, so they gain scientific reputation. We detect that people cite us. We have over 2,400 citations in the literature, and people asked us whether this can be research, this infrastructure can support research, and therefore we started to track the secondary citations, and there's been over 55,000 secondary citations to these 2,400 papers, which would have an H-index of 106. So research can be done in an infrastructure like that. And also education can be done. And I'll show you how we track down education impact. We have over 54,000 students that have used nanoHUB systematically in a classroom in over 5,000 classes at 185 institutions. And this material can be rapidly adopted into classrooms in less than 6 months. And I'll show you some of these adoption rates as well. Now, that being said, we have changed fundamental approaches and underlying assumptions. We can use a cyber infrastructure like this for research and for education, and we change this into new paradigms, and that's what I like to highlight here. So, we want to go beyond specialized capabilities in nano, and I'm going to show you an example of something that is pretty old. Look at this. This is the first vehicle with an auto engine or a gasoline-powered engine, and it looks pretty much like a coach, but if you look at this, this was a very specialized vehicle. Only few people in the world could afford it, and the driver was not only the driver, it was the mechanic, it was the gasoline fetcher, and it had to upkeep this car for this very rich person. What really changed cars was the innovative usability and accessibility that Ford provided, and that truly had impact. Now, we have seen similar examples that are more recent. For example, tablet PCs have been around, but what really made the difference was the usability of iPads and little notebooks that anybody in the world is using now. Now, something similar has happened also in these scientific engines and tools that we use. I'm familiar with NEMO. I helped to create the nanoelectronic modeling toolkit. There's many other engines that we have in nanoHUB now that might be familiar to you if you're into material science or quantum simulations or material simulations. So what we have done is we have turned these complicated engines that are very much similar to this car, and we've turned it into something useful, because this car is very similar to these simulation engines. And you might say, well, you have this graduate student up front, and the steering wheel is an X-term. And the car is really a supercomputer with limited accessibility. And the big fat guy in the back is me, the professor that is driving the graduate student, right? Meanwhile, the graduate student is really driving me. So what we've done in nanoHUB is really make these tools accessible through user interfaces, and broad audiences can utilize them now. And we've seen significant growth as we made these tools interactive and accessible. And that's the story I'd like to tell you about interactive, usable tools that are now being listed in the Web of Science as proper publications. As I mentioned, I have my own experience in building tools and engines. That's the Nanoelectronic Modeling Toolkit, where we model transport through electronic structure and electronic structure of millions of atoms in a quantum dot or ultra-scale transistors, etc. So the key element I want to drive home here is usability to create innovation. And I'd like to drive that home with some numbers. And I'm taking some really old slides that I've pulled out from 2010. So here's a tool that's an industrial strength tool called Padre. It's a simulation engine that can model semiconductor devices to a very high degree of detail. And you'd have to learn the gobbledygook language to operate this tool. We have it on nanoHUB. What we also have is some visualization on top of these engines that where you can compare results, etc. So we added some usability aspects. But we've also done the following. We've taken the same engine and made an app out of it. And we enabled people to model transistors like this in an app-like form. And we've done this for multiple of these apps. For MOSFETs, for MOSCAPs, for PN junctions, for BJTs, drift diffusion models. And even 10 years ago, when we started kind of doing this, we can compare the number of users. So we had 900 users on the complex engine that demands that you learn the language, and some 6,000 users that are using this in apps. So significantly a larger number of people like to use these apps. Now, 10 years later, we've seen the trend more dramatically evolve. More and more people want to have these apps. And we really created the first app store for nanoscience on nanoHUB. And that's what these numbers show you, that really users like to have end-to-end apps rather than these engines that require specialized knowledge. Now, the GUI, the graphical user interface, is really important. When we switched from web forms that we used to have, just like what your bank still has today, to interactive apps, we've seen a dramatic growth. And what I'm showing you here are the monthly numbers of a particular tool set, and you see some spikes. Those are some poor students that were suffering through some classrooms. And as we made the tool more interactive, we've seen a dramatic growth. And that growth was significant, and we didn't announce it anywhere, just people show up and use these kind of tools. What's even more exciting is that the number of downloads of the source code dropped dramatically because people really don't care about installing software and maintaining it. So the key message is really usability. Now, once you have usability, you might want to do more things that enable other people to use it. And this trend of broadening participation is something similar that you've seen from simple iPhones and now iPads and even more, where people argued in the very beginning that the iPhone and the iPad have processors that are inferior, smaller than what the more powerful engines can do. But what really was the key element was the capability and usability combined. And that is what we're trying to do with nanoHUB and put into people's hands. All right, so how do we know what people do? So here is an example of how we do a user analysis. We stack users that are behaving similarly together. So on the horizontal line, you see here time, and we stack together people that are behaving similarly. So here's a group that comes throughout a whole semester. Here's a group that uses 1 tool, 2, 3, 4 different tools over a segment of time. And here's yet another group that is more scattered, smaller group. So we can identify by user-user correlation classroom behavior. And we've, of course, validated that by contacting faculty members and validating our models where we can extract classroom behavior. So now that we know people use these tools in classrooms, we can say this purple tool here is a tool being used in classrooms. If it's used in lots of classrooms, we can develop a scale where we rank these tools on, say, an educational use scale. And if you're down here at 0, well, you're not being used much in education. If you're up here in 1, you're being heavily used in education. Lots of classrooms, lots of people using it. I mentioned briefly before, we study social network charts of papers that cite us, so we can rank the tools that cite nanoHUB, and we can rank them on an on a research axis. So if you're down here, you're not being used in research. If you're up here, you're being heavily used in research. And people think that these two axes are orthogonal to each other. They really do think that you are either in education or in research. And the data that we can now show is that indeed we're bridging the gap. The tools we have are really being used in research and in education. Of course, there's specialized tools that are only used in research, and some tools are only used in education. But by and large, there's a dual use of education and research. And the really cool thing I want to share with you now is that I can look back in history when these tools were created back in time, and look, since the year 2000, we actually have data of doing this. So a tool starts out here in the origin where we don't know what the usage is going to be. And then we track it in our model in terms of research use and education use. So early on, it was hard to put tools into nanoHUB. There were web forms. Number one, it's hard to put them in. It's hard to use them. They're not very user-friendly. NCN, the organization I represent, was created in 2000. And then we created a new software system called Rapture that allowed us to have interactive apps that can be easily installed by researchers themselves. And suddenly, you have a lot of tools pop up. And what's interesting is that they pop up on the research axis, and they eventually drift also into the education axis. So really, that is the typical thing you would expect a research university to do. And we have now a platform that is shared across the world, and it's free, that allows researchers to share their codes and migrate them into educational use on a broad scale. So I would call this truly translational with longitudinal data that we do have available now. Now, I can also measure the time to adoption. Since each tool has a digital object identifier, sort of a birthday, if you will, I can measure the time from the birthday to the first occurrence in a classroom. And I can compare that to some more traditional time scale, like writing the second edition of a textbook, which typically takes about 4 years. And I'm putting this on a rather non-linear scale here, reaching down from years to weeks, because we can show that some of the tools show up in weeks, months, and 3 months in a classroom. In fact, the median time when we measured this years ago was less than 6 months for a tool to be published on nanoHUB and showing up in a classroom. So that is really rapid adoption of research into classrooms for education innovation. Now, that all being said, I want to leave you with the vision we have for nanoHUB to accelerate innovation through user-centric science and engineering. And we want to make science and engineering products that are usable, discoverable, reproducible, and easy to create for learners, educators, researchers, and business professionals. So with that, I thank you very much.